All right, we'll continue with number 6, which says, which is the smallest quantity? So let's look at each one of these, and then we'll map them out on here, and we'll see approximately where they are. So the energy of a photon with a wavelength of 100 meters. So here we are in meters right here, and 100 meters would be off the chart because it gets to 10 meters here. So 100 meters would be like way over here, which if we drop down to the energy value right here, we'd be 10 to the negative 24th, negative 25th. You'd be like 10 to the negative 26th. That would be the smallest one way over here to the left, unless we find something with a larger wavelength than that. Okay, let's see, an energy of a microwave photon. So here are the microwave photons right here. So those would be somewhere in here, like 10 to the negative 23rd or so. Energy of a photon with a wavelength of 100 centimeters, which is 0.1 meters. So finding meters right here, 0.1 meters is right here. It looks like that one right there would be like 10 to the negative 24th, which is actually a smaller amount of energy than this one. An infrared photon, so here's infrared right about here. So that'd be on the order of 10 to the negative 20th would be this. So it'd be a little smaller than that. So it'd be closer to 10 to the negative 21st. And then lastly, energy required to break a typical chemical bond. Well, you know from number 4 right here that the wavelength needed to break that photon was 316 nanometers. And 316 nanometers was like right in here or so. And so you can see that that energy would be 10 to the negative 18th. And so that would be much larger energy than 10 to the negative 20th or 10 to the negative 21st or 23rd or 24th or 26th. So E right here, the energy needed to break a typical chemical bond, would be the largest of the quantities. This would be the largest. And then the smallest quantity would be the energy of the photon with the 100 meters wavelength right here, which would be 10 to the negative 26th, which would be A, which would be the smallest right here. And so it says, which is the smallest quantity? Letter A right here would be the smallest quantity. The largest would be letter E. You should be able to be prepared to answer either of those questions, which is the smallest and which is the largest. And now you can see what order they were in. Turning the page. Number 7, this particular one is not on this year's exam. Then it says, I can determine the energy level, sublevel, orbitals of multi-electron atoms, including electron and orbital notations. All right, so each d sublevel can accommodate blank number of electrons. So I'm just going to turn the page here in your textbook to where it talked about d orbitals. This is what d orbitals look like, and notice there's 1, 2, 3, 4, 5 of them, and each orbital can hold 2 electrons, and so 2 times 5 is 10. So each d subshell can hold 10 electrons total, and each set of orbitals can hold 2 each. So A right here for the subshell or for the sublevel. Use the following answers for the next 3 questions. They can be used more than once. Blank have orbitals that are a dumbbell shape. So p orbitals right here are the dumbbell shape, which is B, p orbitals. Blank orbitals have a spherical shape. So if you back up a page right here, you can see the 1s, 2s, and 3s orbitals, and they're spherical in shape. So those would be C. Blank orbitals have 4 different orientations and 1 different shape. Well, here's 4 different orientations, and then 1 different shape that has a donut around the middle as well. So those would be your d orbitals. That would be letter D for d orbitals. Number 16, the principal quantum number n for the outermost electron in the bromide or bromine atom is. Well, first of all, what is this thing called a principal quantum number, or the letter n? Well, n are these numbers right here. N equals 1, 2, 3, 4, 5, 6, 7. And you might say, oh, those are just the period numbers. Yeah, the period numbers are also known as the principal quantum number, or letter n. Some people call them the highest energy level as well. So these numbers right here are n, or period numbers, or principal quantum numbers. So in bromine, you can see bromine is in the 4th period. Therefore, the highest energy level for electrons is the 4th principal quantum number. So D4 right here. There is our blank orbitals in the first subshell. So the first subshell, remember, just contains 2 electrons, hydrogen and helium's electrons. It's in the first period, and it just has the 1s orbital. So there's only one orbital. It happens to be an S-shaped orbital. If you are in n equals 2, well, then you'd have the 2s, and then you would also have the 2p orbitals. So you'd have a total of 4 orbitals in there. 3 from the 2p and 1 from the 2s. Use the following answers in the next 3 questions. They may be used more than once. The blank subshell contains 3 orbitals. So the subshell that contains 3 different orbitals are the p orbitals, and so that would be the 2p right here, letter A. The blank subshell contains 5 orbitals. Remember, the 5 orbital containing one looks like this, and these are the Ds. And so you have to find one with a D in it, and it could be 3D, C, or it could be 5D. It could be E. So 2 possible answers there for that one. Both are correct. And then number 20 we're at. The blank subshell contains 7 orbitals. Well, I don't have a picture of that one. I'll see if I can come up with one in just a second. But the F orbitals right here, the D, F orbitals right here, contains 7 different orbitals. So 1, 2, 3, 4, 5, and then 2 more along with it as well. And the last one that we'll do in this video is blank is the electron configuration of a blank atom right here. So Kr, that would be our core electrons, so find krypton right here, and then 5s1 4d10. So notice how it tricks us, and it tells us that it's just a 5s1 and then a 4d10, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 would put us right about here, but notice we missed an electron right here because we went 5s1 and then 4d10, and it turns out that those 10 electrons then would be this electron promoted to this area to fill these guys up right here, and one of them would fill this space as well, and so this would be Silver's arrangement. So let's just go to a place where we have a few exceptions to this electron configuration, and let's note a couple of those strange exceptions. And you can see in the anomalous configuration area that you have the silver right here being 5s1 4d10. You can see copper also does that, 4s1 3d10, even though that you normally would think that this would be 5s2, 5s2 1 2, and then 4d9, and this would be 4s2 3d9. But notice it takes one electron from here and promotes it into the d sublevels to make those filled. You'll also notice that that happens right here in chromium and molybdenum right here, that only one of the s orbitals gets filled, so then you can have a half-filled sublevel of 3ds and a half-filled sublevel of 4ds right there in chromium and molybdenum. You'll also find some really strange exceptions down here in the F areas as well. And notice how they put these Fs, which are supposed to go right here, down in this area like this. And so the lanthanide-actinide series actually fit in this area.